That's because you're not studying effectively. So I'm not saying you're not studying. You're not studying the way you need to study. And that takes a little bit of practice learning how to do that. Unlike other courses, studying physics is all practice. It's like practicing a musical instrument or practicing a sport. If you don't practice it, you're not going to get any better. A lot of you I know are just going home and looking at your notes, looking at what I did with you, either in class live or from a video. That is not how you study physics. The way you study it is you go back to the questions we did together. You cover up the solution and you try it again all on your own. And if you can get it right after you've done that, then you know what you're doing. Otherwise, you don't know what you're doing. When I do stuff with you in class, it's going to look easier than when you do it on your own. Why? Because I've been teaching physics for 27 years, and my first physics class was in 1988. I've been doing this for a very long time. So it better look easy when I do it. I know what I'm doing because I've been practicing it for 35 years. I'm not expecting you to do it as quickly as me, but you do need to practice it so that way you can get better. That is the only way. Think of physics as a skill, not a subject. You don't learn skills by just reading things. It would be like me watching the NFL games on TV and expecting that I can go out to the field and throw the football just like all of them. You think that's going to happen by just watching? No way. And right now, that's what you're all doing. You're watching us do things in class and expecting that when you get to the game, you can play like a pro. Unless you practice it yourself, it isn't going to happen. And that's more than just 5 minutes a day. Homework is part of that, where you're putting in a really good effort into doing that homework. And when you struggle, you got to ask for help, either from me or from Mr. Walter when he's in for me, or from another student who's really understanding what's going on. And if you feel like you need a tutor, you reach out to me. I have a whole class of AP Physics students who got above a 95% on the Regents exam who are willing to help you because they need to do that for National Honor Society anyway. And they love physics. That's why they're taking it a second year, and they are willing to help you. They need it. You get a benefit by learning. You're not paying them anything. They're getting a benefit by getting their tutoring hours that they're required to do for that organization. Okay? So you have to take some of that responsibility for yourself. There's no way I can chase after you for this. Your grades from yesterday's test are posted. You're not looking at them now. It's over. Except when you get it back and you are eligible for test corrections with the multiple choice. Then you'll have a week to correct it and get it back to me with a parent signature or guardian signature, somebody at home. Okay? That's the only way your grade's going to improve. That and lab corrections. All right, enough of my lecture. Let's get into Unit 3C. We're going to talk about calculations today, which involve position time graphs for accelerated motion. Remember that we learned last week when you were learning section B of Unit 3, that whenever you have a graph for accelerated motion, and it is a position time graph, you're going to see a parabola. A parabola on one of these graphs indicates that you have acceleration. Now, there are 3 kinds of calculations I expect that you can do from a graph of position versus time. The first calculation is a calculation of displacement. And remember that we learned in Unit 2 that displacement is simply a change in the position. It's a change in the y coordinate of this graph. So that's pretty easy to do. You just read the 2 y coordinates and you subtract to get the displacement. Then we're going to learn how to calculate 2 different kinds of velocity. One is called an average velocity, and the other is called an instantaneous velocity. And these are actual calculations. You're not just reading a graph. All right, so let's review these things that we should already know. On a position time graph, remember that position is going to be on the y-axis. That is your dependent variable, and time is on the x-axis. It's your independent variable. And as we discussed in Unit 2, you find the displacement by looking at the change in the y coordinates. Remember, this symbol, you learned this in math, means change. You're looking at a change in the y coordinates. What are the y coordinates on a position time graph? Those are position values. So you're looking at a change in the position values. In other words, you look at it as how far up does the graph go from where it started, or how far down did the graph go from where it started. We also learned in Unit 2 that we can find the velocity on a position time graph by looking at the slope. Now, the thing was, in Unit 2, all of our position time graphs for constant velocity were lines. And what you now have seen from Unit 3B in this is that these graphs are no longer lines. When you have a speeding up or slowing down type of motion, the graph either gets steeper over time or shallower over time. You can't find slopes of curves. The slope equation only works for a line. So there's got to be some things, other things that we have to think about besides understanding it's just a slope, especially because when we accelerate, the magnitude of our velocity is going to change, and maybe our direction of our velocity will change too. So let's just review how we did slopes in Unit 2. We had an equation that we wrote on our reference table on page 7, the blank page at the end for slope. Rise over run, change in y over change in x. So what we learned in Unit 2 was that when we calculated the slope, if the slope was a positive 4 meters per second, that meant that we were moving in the positive direction, which is usually to the right for this unit, at 4 meters per second. If we had a slope that was negative 8 meters per second, that would mean that we were traveling to the left or in our negative direction at 8 meters per second. If we had a slope that was equal to 0, in other words, the line was horizontal, that meant we weren't moving. That's still true. We're still going to see graphs of constant velocity or no motion. But now let's talk about what happens when we have that curve, that parabola on a position time graph. And this is just, again, more review. When you have a diagonal line on your graph, your position time graph is diagonal. That meant our velocity was constant. Why was our velocity constant? Because the slope of a line doesn't change. It's the same no matter where you are on the line, and the slope is our velocity. So the velocity isn't changing either. Now, you watched a video back at the beginning of Unit 2 about the difference between speed and velocity. And they talked about different kinds of velocity, an average velocity and instantaneous velocity. What we're now going to learn is that slope that we were finding was actually an average velocity. What do I mean by average? It means that, you get a 50 on one test and a 75, or I'm sorry, let's make the math easier. A 50 on one test and 100 on another test, what's the average? 75. It's kind of in the middle. But if I get a 50 on one test and a 50 on another test, what's my average? Still a 50. When things don't change, the average is the same as those individual values. And that's what we were seeing when we did Unit 2. The velocity didn't change, so that slope, which was our average velocity, is the same as our velocity at every time, which we call instantaneous velocity. So now let's discuss what we're going to do with these curves, because there's a couple of things you have to decide when you read a question about a calculation of velocity on a position time graph. So the slope is still going to be velocity. The units of the slope on a position time graph are still going to be units of length over units of time, meters per second in the metric system, which indicates that the slope is still going to be a velocity because velocities are measured in meters per second. But since you have a curve, the slope will not be constant. It's going to change as you move along the curve. And it's going to depend upon where you are on the parabola. So since the slope is changing as you move along the parabola, that means that the instantaneous velocity of the object is changing. And what does that mean if your velocity is changing? It means that you are accelerating. That is the definition of acceleration that you learned back in Unit 3A. That an acceleration is a change in velocity over time. All right, can I go on? All right, I'm not seeing any no's, so I'm going on. So what I'm going to do now is show you a video clip of zooming in at one point on a parabola. And my question is, what are you noticing on this parabola as we zoom in at this one point? Okay, let me see. Hopefully this is going to open for me. Yep, there we go. Okay, so on this graph in pink is the parabola. And I'm zooming in, increasing the magnification at that point marked in red. What are you noticing happening at that point as we increase the magnification? What does that mean? What does it start to look like? Starts to look like a line. We can only find slopes of lines, right? We said that earlier. We have established that in your math classes. You can only find the slope of a line. So when you have a parabola, like we're going to see for these accelerated motion graphs, we can actually find the slope at a point by imagining that there is a line at that point, by imagining that you are zooming in, like you might do on your phone, right? You just pinch, you expand it, so you're zooming in, and then it starts to look a lot like a line. So that's going to help us understand what to do. So when we look at a point on a parabola, that very, very, very tiny section starts to look like a line. And as we've said, we need a line in order to calculate slope. We need a line to help us calculate slope. So this is going to give us a strategy to help us make a line on this parabola that we can then find the slope of to get a velocity. Now, if I go back to that animation for a minute right here, you'll see that there is that line already drawn next to the pink parabola, this one here. Anybody know what that line, type of line is called? I'm not asking for the shape. That's a diagonal line, obviously. I want to know what that type of line to a curve is called. Anybody know? It starts with a T. Yes, it's called a tangent line. It's called a tangent line. We're going to be learning how to draw tangent lines to parabolas in our method, in our strategy that we're going to talk about now and what that's going to give us. So let's talk about this strategy. You can see here I have a parabola and I've drawn a line at that point. That line is called a tangent line. So this is what we're going to do. We're going to draw these tangent lines to our position time graphs if you are asked to find an instantaneous velocity. Now, what do I mean by an instantaneous velocity? I'm talking about the velocity at one particular moment in time on the graph. So if you're asked to find an instantaneous velocity, like the velocity at 5 seconds, that's an instantaneous velocity. What you're going to do is draw a tangent line to the parabola at that time. The example I just said was 5 seconds. Draw a tangent line to the parabola at 5 seconds, and then find the slope of that tangent line. So on this example that I'm showing you here, this line drawn in blue is the tangent line. And it was drawn, if I read this graph, this is 0.8 seconds. So this would be 1.0, 1.2, 1.4, 1.6 seconds. This tangent line is drawn at this time point on the parabola, which is 1.0 seconds. So this student was asked to calculate the velocity at 1.0 seconds. I'm not going to say find an instantaneous velocity. I'm going to say find the velocity at one time. That's what is meant by an instantaneous velocity. So this is a different kind of line. You see I've got a parabola there drawn in blue. There is a line there which is connecting 2 points on the parabola. This time and that time. That type of line is called a secant line. When we draw a secant line that connects 2 points on the parabola, what you are finding is what's called an average velocity. It's like the middle velocity between those two times. So as we talked about a little while ago, if one velocity here was 50 meters per second, and the velocity there was 100 meters per second, you would be finding the middle velocity, the average of those two, which is 75 meters per second, just like with an average test. So that change in position over time between those two time points, which is the slope of the secant line connecting those 2 points, is what we call an average velocity. And a question would say, calculate the average velocity between 0 seconds and 5 seconds. That's what it would say. It would actually say average velocity, and it would give you 2 times. When you see that, you have to know, oh, I have to draw a secant line and find the slope of that. If I just give you 1 time, then you're finding an instantaneous velocity, and you need to know, oh, I have to draw a tangent line and then find the slope of that tangent line. That's what you have to do. Those are the calculations you'll be asked to do in this unit. Okay, is everybody set with these? Okay, so that means we can now start to practice this. So if you could please take out your Unit 3 packet. Keep your notes out so you have a reminder of what to do. You're also going to need a ruler today. So keep out your notebook, keep out your pencil, take out your ruler and your calculator and your Unit 3 packet. Because now we can start practicing the concepts that we just discussed. I do not. I don't loan them out. Nope. Not unless yours is broken and you can show me you have a broken one. We have to be prepared for class every day. You have to bring all your materials. All right, could you all please turn to page 14? And on page 14, you're going to see this displacement time graph given to you. Everybody with me? Before we do any calculations with this graph, let's do a little review. Right now, based upon what you learned in class last week, you should be able to describe for me what this object is, how it's moving. Let's see if you can do that. And let's add that here. This is not a pencil. I thought it was a pencil. That one doesn't work well. Oh, it's not the ones I want. I want my nice pencil. Simple pleasures in life. I want the pencil that I like. You all have a favorite pen or pencil? Yeah. I'm particular about my pencil. There we go. Okay. So let's start with our description of motion. First thing, is this object moving? How can you tell? Because it's not a what? It's not a horizontal line. Okay, so it's moving. So my next question, like yesterday's test, I had broken it down. Little steps. You should be able to tell me in what direction it's moving, since it's moving. Is it moving right or left? It's going right. How do you know it's moving to the right? Yeah, the graph's going up. That's how you know it's moving to the right. The graph is going up. So let's start with it's moving to the right. Now, how is it moving to the right? Like yesterday's test, I said, is it stopped, constant speed, speeding up, or slowing down? Those are your only options. We already said it's not stopped because it's not a horizontal line. Is this a constant speed? How do you know it's not a constant speed? All lines are straight. It's not a what kind of line? Starts with a D, diagonal. It's not diagonal, so it's not a constant speed. 50-50. Is it speeding up or slowing down? Speeding up. How do you know? Because the graph is getting steeper. So this is moving to the right and speeding up. Now, how did we know that? We said we know it's moving to the right because the graph goes up. And we know that it is speeding up because it gets steeper as time goes on. Those are the patterns you need to be able to recognize. And yeah, that does involve a little bit of memorization on your part. You have to understand the patterns in order to explain these graphs. Okay, let's just talk about what that means in terms of the signs of our velocity and our acceleration, which is also a review from last week. If you are moving to the right, would your velocity be positive or negative? Ryder? That's correct. This means that we have a positive velocity because this graph is going up. All the slopes are positive. Now, when we speed up, you should have this in your notes. When you speed up, your acceleration is always the same sign as your velocity. So what sign is the acceleration? Positive, because that's positive. Only when you slow down do these become opposite signs. Opposite signs means slowing down. Same signs, no matter what those signs are, means speeding up. Okay, now let's talk about the two types of velocities I'm going to ask you to find on this graph. We're going to tackle the easy one first. Let's say the first question I'm asking you is to calculate the average velocity between 0.00 seconds and trying to find a good time point. 1.00 seconds. I want us to calculate the average velocity between 0.00 seconds and 1.00 seconds. And I'm looking for average velocity. All right. So what am I going to do? I got to draw a line, because any type of velocity that comes from a graph of position time or displacement time, displacement's just change in position, deals with a slope, but you need a line. I don't have a line right now. Based on your notes from today, what is the type of line I'm going to have to construct on this graph, since I want average velocity? Janicia? Correct. We need a secant line. You have to know that. You need what's called a secant line. What is a secant line? It's just a line which connects those 2 points on the graph. These are the 2 points I have to look at. 0 seconds, which is here, and 1.00 seconds, which if I read my graph, here's 1.00, it's here. All right, you have your ruler? Construct a line which connects those points. It does not need to end at 1 second. It just needs to connect them. You have your ruler? Let's do it. Connect those 2 points. Notice I am extending my line well beyond those 2 points. This type of line, as we said, is called a secant line. That line we just constructed is called a secant line. All right, so what are we going to do now? We're going to find the slope of that line that you just constructed. To find a slope, you need 2 points on the graph on that line. I'm going to use that point as point 1 and this point as point 2, because that falls right where 2 grid lines intersect, so I can easily read off their coordinates. Remember how we do this? We list the coordinates of each point. Point 1 is this one here. The x coordinate is 0.00 seconds. The y coordinate is 0.00, and the units on this graph on the y-axis are centimeters. Now I'm going to do the same thing for point 2. Point 2's x coordinate is 1.00 seconds. The y coordinate, I have to come over, it's right here. I believe that's 50, 60, 70, 80, 90, 100. So every line is 5. So this would be 55, 60. That would be 65.00. I keep the same precision as what's on the graph. So 65.00 centimeters. Now, the symbol for average velocity is what we call V bar. V bar. We put a bar over it. If you look at your reference table, and this is where I want y'all to just quickly look at your reference table for a minute. You'll see that here, you see how we define average velocity or average speed? There's a bar on it. This is the vector, that's the scalar. So I could put an arrow over it as well. V bar with the arrow over the top is average velocity. Do you see that? These are going to be measured in meters per second, just like any instantaneous velocity or speed. V bar is your average. We always add a little line over the top. If it's a velocity, I'll put an arrow over it as well. So I'm going to add an arrow over the top of that. So V bar with the arrow. Now, what am I going to do to get that? I'm going to find the slope. which is y2 minus y1 over x2 minus x1. That formula should look familiar. I'm now going to do my substitution with units. Y2 is 65.00 centimeters. Y1 was 0.00 centimeters. X2 is 1.00 seconds. X1 is 0.00 seconds. And then we learned, let's do the intermediate subtraction, giving me positive 65.00 centimeters over 1.00 seconds. Now I can pay attention to units and sig figs and direction. So when I divide that out, I'm going to get positive 65.0 centimeters per second for the average velocity. Why am I only using 3 sig figs? Because the numerator had 4, the denominator had 3, so I have to reduce my answer to 3 significant figures. Since velocity is a vector, I do need that positive sign. Okay. Everybody good with that? All right, let's try the other one that we learned how to do today. The other one we discussed doing was finding what we call an instantaneous velocity. So the question is now going to say calculate the velocity at .75 seconds. Do you notice there's only one time given to you right now? Only one time. That means we're going to have to draw a tangent line to that curve at that time. This is what we call an instantaneous velocity, a velocity at just one time. There's only one time given, it's an instantaneous velocity. So what I'd like you to do is find where that time point is on the graph. Can you do that? Each of these, I believe, is 0.05 seconds. So 55, 60, 65, 70, 75, 80, 85, 90, 95. Yep, that will work. So that means I'm looking at that point right there on my graph. This is 0.75 seconds. Now, what I'm going to do is something that you can't do. I can actually zoom in at that point because I have a camera on that point. Right? I could do that. When you do it, you have to envision that, right? And kind of zooming in, and what do you see? So I'm going to zoom in, way in. And if I look at this point, I can pick a point right here and right here. In between those two little marks I made, doesn't it look like a line in there, like a little line segment? That's actually how computer-generated images are created that are curves. They stitch together teeny tiny little line segments all the way. What we're going to do is connect those two little marks that you can make and just extend them really nice and long. So let me zoom back out so you can see what I mean. All right, can you see those two little marks? Make them yourself on either side. Then take your ruler, and I want you to connect those points. This line that I am now constructing, you see how big I made it? That is our tangent line. That's our tangent line. And that is the tangent line drawn at 0.75 seconds. That line we have to find the slope of to answer question 2. So how do we find the slope of the line? Find 2 points on it. I'm going to use points where I see grid lines intersecting, like right here. The vertical and horizontal lines intersect right there at that point for me. It may not be for you. This is where everybody might get a slightly different answer, and that is okay. As long as you drew your tangent line approximately correctly, you're going to get these points, or get the credit, I should say. And I'm going to use this point way out here. I like to find them far, far, far apart. That's going to be my point 2, this one here. Those are far apart, and I have grid lines intersecting. I can read those coordinates off. So I'm going to do the same thing I did previously. My givens are for point 1 and point 2. All right, now I got to figure out what the time is for point 1. For me, point 1 is at 0.40 seconds. And that is 0.05 centimeters. My second one here, let's see what that time is. 110, 20, 31.35 seconds. Label that 1.35 seconds. And now I got to get the y coordinate, so I'm going to read over right here. That would be 90.00 centimeters for me. That's where that is. Okay. The symbol for velocity is just V with the arrow over the top. No bar. That distinguishes an average from an instantaneous value. V without the bar is an instantaneous value. What equation am I going to use? I'm going to use my slope equation, that the velocity is y2 minus y1 over x2 minus x1. I'm now going to plug in those coordinates. So 90.00 cm minus 0.05 cm all over 1.35 s minus 0.40 s. I'm going to do my intermediate subtraction. So the numerator gives me positive 89.95 cm all over 0.95 s. Let's talk sig figs. My numerator here has 4 sig figs. My denominator has only 2. So when I solve this now for that velocity, I'm going to round my calculator answer to 2 sig figs. So I'm going to take that calculator answer and I'm going to round it to 95. Positive 95 centimeters per second. And that is my instantaneous velocity at 0.75 seconds. That's how fast I was moving at 0.75 seconds. I was traveling to the right at 95 centimeters per second at that one time, based upon the tangent line that I drew. Are you going to get exactly that? No, but you should get something close. It all depends on how exactly you drew your tangent line. So what I have to do is look at your tangent line and say, yeah, that looks pretty good to me. And then I have to look at those 2 points you selected and make sure you wrote down the coordinates correctly. And if that's all good, then you got the credit. Okay? That's all we're going to do with this today. We're going to practice this more tomorrow. After our break, we're going to start Lab 7, which is a Chromebook lab. So you can grab your Chromebooks. If you need to get a charger, you can do that. But let's get set up for that during break. Use the restroom if you need it now, please. Yes. For maybe. I'm not sure I'm going to be here. I'm going to talk about that next period. You have early dismissal? You have a at 9:20. Okay, so what you're going to want to do is make sure you watch the rest of the video in today's recording so that way you can get caught up with the one. Okay. Yes.
How did you allow me the final answer? You did 266
Because my time had only 2 Pacific rule. You don't look at the individual values, you look at what you get after you subtract for the sig figs, because you got to keep precision.
Okay, so I should just keep 88.
Yep, positive 88.
There's no way. I'm that good. Huh? I'm actually happy.
What do I want to share? I want to share this.
I studied for 2 hours. Oh, now I'm just scared. I'm just scared for my AP coverage.
Oh, you have that too?
Bro, I told them at midnight. I'll just stay until like 11 and 12.
You're done your senior. You do that thing for me. Just take a long time.
Yeah,
A lot of time.
I don't know. I kept this for the we didn't talk too much. I didn't. He just told me.
Yeah. She probably got
She told me that. I feel like
No, I was in Texas, so I didn't start. They
say the word, right?
they didn't text academic.
Yeah.
Folks, you just need your Chromebook. You can put everything else away. Just your Chromebook. All right, so on our Google Classroom, you'll see that lab number 7 was pushed out to you today as an assignment. I'd like you all to open up that lab. It will look like this Google Sheet. And we're going to use the same PhET simulation that we used for lab number 5, the Moving Man lab. Difference is I'm here to get you started on it this time, so hopefully we can do a little bit better with that. Although the video walked you through how to do all of lab 5. So if you followed the video, you should have done fairly well. So I'm going to open up that PhET simulation as well. It's linked in the Google Sheet, but it's also linked in the assignment. So just open that up. This is the simulation. I'm going to make this a little bit smaller so I can see everything on there. Why isn't it showing the acceleration piece? Let me refresh it. See if it will show me. For this simulation, we're going to need 3 variables at the bottom to adjust. There they are. We're going to need the position, the velocity, and the acceleration. Okay, you're going to need all 3 of those. So if that's not showing up on your screen, all 3 of them, position, velocity, and acceleration, in your Chrome tab, if you go to the top right, where you have these 3 dots, you can change the magnification on the screen right here with the zoom. You can see mine's at 80%. You can shrink it if you shrink it and then refresh your screen, it should then show you all 3 sliders: position, velocity, and acceleration. If you have all 3, you're all set. Okay, is everybody all set with that? So you have the simulation open and you have the Google Sheet. Yes, we're good? Okay. I'm not going through the setup because it's the same setup as we had with the last lab. And you've all at least started that lab. Some of you still need to get it turned in. It is now late. Way late. It was due a week ago. So you're losing 50% credit when labs come in late. So here's the thing, unless you're absent. You're absent when we do a lab in class, then you get a little grace, but you're not getting 3 months of grace. You get like a couple days because I know you're making up stuff for everybody. What we're going to do in this simulation is just follow the directions in the 3 parts of the lab. Part 1 is all about collecting data. And you'll see that as you look through part 1, there are 4 different motions we're going to be looking at. Motion 1, you can see it on here on the screen, says we're going to be looking at, I'll make this a little bit bigger. We're going to be looking at a man speeding up as he moves to the right. Then we're going to look at him speeding up as he goes to the left. Then you're going to look at him slowing down as he goes to the right. And then you're going to look at him slowing down as he goes to the left. Notice you have all those shaded cells to fill in with the position and velocity values. Once you've set him, you're just going to follow the directions. Just set up the simulation to have these variables typed in, starting at a position of 0 meters, velocity of 0 meters per second, acceleration of positive 0.5 meter per second squared. Click play for 5 seconds, and then go back and record the data for every half a second. You're going to do that for each of them. Just follow the directions. Don't do anything yet. I'm just showing you what to do because then I'm going to turn you loose to finish this. I won't give you any further instruction. Part 2 is where things are going to get really interesting. You see what it says right at the top of the part 2 sheet? You should have it on your screen too, in blue. Don't edit the data in those tables. The Google Sheet has formulas behind it to take all the data you did in part 1 and put it in these data tables. So if you need to edit any of the data, it's wrong. Where are you going to go? Part 1 and fix it in part 1. You'll get 2 data tables here, one for position and time, and then a second one for velocity and time. And after you have all of your data, those 2 tables are going to be filled in, and then you're going to make some graphs. You're going to make a graph that is a scatter graph. I'm telling you what type of graph to select when Google Sheets makes the graph. It's not going to give you a scatter graph. It's going to give you bar graphs. So we've learned how to edit bar graphs before to make them scatter graphs. You're going to have to do that. But here are the parameters you need to make sure appears on your graph. It says that you need all 4 motions on the same graph, that you need a title on it. You need the X and Y axes, variables, and units labeled appropriately. You should know appropriate scaling. That means you have a 0, 0 on the bottom left corner clearly visible. And you should know how to set it if there isn't a 0 there. You need the trend line added to the graph. You need the equations for those all 4 motions, and then a legend which tells you which color, line, or curve corresponds to which motion. This is motion 1, 2, 3, 4. And then you're going to put your graph there. And then you're going to do the same thing for the velocity and time. You're going to make a velocity time graph. That is a scatter graph type with all 4 motions on the same graph. It's got to have a title on it. The X and Y axes should be labeled with their variable name and the units. You should have appropriate scaling. That means we see a 0, 0 on the graph, not a point, but we can see that where the origin is on your graph. We have to add our trend lines, our equations, and a legend, just like the other one. Once you have the graphs, you're then going to go to the conclusions, and you're going to fill in the blanks. Looking for the patterns. You should already know those patterns, because where are those patterns? They're in Unit 3B. So if you need help answering those questions, you're going to need to look back in your notes for Unit 3B. You don't have the notes? Guess where you get them? In Google Classroom. There are copies of all the slides from my presentations for all of Unit 3 already posted in Google Classroom. You can get them there, or you can go back and watch the videos again and get what you missed. It's on you. You have to do that. I can't do that for you. All right? Any questions on what you have to do? You're going to get 2 full class periods to get this done. I hope you can get all of your data and both of the graphs done today. And to help you out with this, I'm going to ask you to pair up with somebody. And you can work on the entire lab with that person. Pair up, help each other. And if you're working on it in class today and you're getting stuck, guess what you do? Miss Veloso, can I get some help? Yes, of course I can help you. I'm here. Okay. Now I just want to talk to you about one thing. I'm here this week. I'm not sure I'm here next week. Unfortunately, when they did my surgery, we got some unexpected results. And I have now a second form of cancer. And it's a little more advanced. So I'm having all kinds of tests done Monday next week to figure out what my plan is. Right now, they're hoping they don't find anything else on this test I'm having done on Monday morning. If everything is good and there's nothing else that shows up Monday morning, I'm having surgery Tuesday morning to get rid of what we found from the last surgery. They didn't get enough of it out. I'd have to go back in and get more out. But I would only be out for 4 days. I'd be out next week. That, in my opinion, that's what I want. I want not to be here next week because that means they didn't find anything else. If they find something else Monday, I'm here Tuesday and all of next week, and then I have to prepare for a much bigger surgery. And in which case I'll be out for 2-3 months. Okay. Yeah, because if you didn't know, I had breast cancer. That's what I had. And that would require that they remove both of my breasts. If that's what happens. That's what they find. And that requires, it's a very long surgery, and I'd be in the hospital for a few days, and then I can't go back to work for a long time. It takes a long time to recover from that. So I'm hoping, right? Hoping this is not what, it's upsetting to me because I didn't find it before I had my first surgery. And I'm looking at least 1, maybe 2 more surgeries. I don't like that. No one wants to be a pincushion and having all that done. So I'm hoping they find nothing, and I'm good. Either way, the prognosis is still good. It's not like it's spread to other parts of my body. At least that's not what we know of right now. So just keep doing what you're doing. Being good. If I am not here next week, I'm still not dead. I'm trying to be funny. I'm not dead. I'm going to be home going stir crazy like I did last time. So please email me with questions, but you should be getting comfortable asking Mr. Walter questions. I know a lot of you are afraid to ask him stuff. Ask him things. He is a physics and math teacher. He's retired. He's bored. So that's why he comes into sub. Ask him questions. If you need to see him after school, he can probably help you after school too. Unless he does a lot of home instruction for our school district, so sometimes he's working at the library, the Colony Library, in the evenings doing his home instruction. So I just need you to start relying on, you have a lot of resources available to you. I'm still at home on email. Kiara and I had a Google Meet when I was home last week. So you can do that too. You want to meet with me? We could do that. I may not look so pretty because I'm kind of groggy on pain meds and whatever, but I'm still doing my things. Okay? I'm watching you on your Chromebooks. It's not called Go Guardian anymore. It's called Apera. So I follow you and I can see your computer screens, whatever you're doing. You know that. Some of you got closed out of things last week where I sent you little notes because I was watching what you were doing in real time. So, all right. So just stay on task, okay? Any questions for me? All right, I'm not trying to tell you things to get scared, but that's just, sorry, sucky. I want to be here. It's not that I want to be out. So I'm going to let you guys do your physics, get your work on your lab. I don't expect you to get it done today. You're going to have 2 class periods, one today and one on Tuesday. If it is not done by the end of the class on Tuesday, that means you were not on task and it will be marked late. unless you were absent, and then you get one additional way. Okay. I don't want to hear, oh, my Chromebook was lagging. I got a bunch of sob stories last time when things came in late. I didn't know I had to finish it. Come on. It was right in Google Classroom. Finish this for homework. All right. So please work on that. Again, partner up, work on with somebody. And when you get stuck, let me know. I'll come and help you.
Acceleration is J. Acceleration is
Remember, you're not inputting acceleration values anywhere. Look at what you're inputting. You are inputting only positions and velocity values. And one other thing, make sure you don't put any units after the numbers you type. You're just putting in the values, the numbers, not the units following them. Okay?
Acceleration.